So we have completed the first part of our chore in extending our results for dust world to a relativistic universe. We have done the kinematics. We have realized how to describe a homogeneous isotropic universe that may be time-dependent, expanding or contracting, in the context of general relativity. Our next step is going to be to see what happens when you apply Einstein's equations, and our first chore, therefore, is we want to describe how gravity responds to matter. We have to see how we will describe the presence of matter consistent with isotropy and homogeneity in the context of relativity. The description is pretty similar. Matter will be described by smearing it out into a homogeneous distribution of energy with constant energy density rho. Why am I saying energy density rather than mass density? Well, because we know that in relativistic theory, gravitation couples to all forms of energy, not just to mass. So, up to factors of c squared. This is the same thing. I will often call rho an energy density, and I will try to keep my factors of c squared consistent when I actually write equations. I also am characterizing matter by a pressure. Why did I not have pressure in dust world? I could have introduced pressure into a Newtonian equations. I didn't, because in the context of the description that we are conducting, the great majority of the energy of both baryonic and non-baryonic WIMPs, dark matter, is in the form of their rest mass. In other words, when you smear out the total energy content in all forms of matter, dark or light, mostly dark, that quarter of the critical density is mostly in the form of the mass of the WIMPs rather than in the form of their kinetic energy. This was a property of what is called cold dark matter models. It is, remember that we said that the WIMPs have a mass about 100 times the mass of a proton. This ensures that under the conditions obtaining in our universe, their motion is roughly non-relativistic, and that means that most of their energy is in the form of their mass rather than in the form of kinetic energy. And for simplicity, we're going to assume that, like the grains of dust in dust world, they're not moving at all, and in fact are stationary other than participating in the overall expansion. We can do this for the WIMPs, but we cannot do this, for example, for the photons of the cosmic microwave background, or if there is a neutrino background, we can't do it for neutrinos. Those particles move at the speed of light, and it is a bad approximation to say that all of their energy is in the form of, well, they don't have a mass, and therefore, for them, it is not legitimate to exclude pressure in the same sense that the momentum of a photon is related by P is E over C to its energy. The pressure for a photon gas is simply related to its energy density by P is rho times C squared over 3. This is true for massless particles, and we are going to discuss explicitly either dust, in other words, massive objects that are essentially not moving, that's what cosmologists call dust, or radiation, by which we mean not necessarily light, but any form of massless particles moving at highly relativistic speeds, or they may be massive, but if their conditions are such that they move at highly relativistic speeds, most of their energy is in the form of their motion rather than their mass, and we will approximate it then by pressure determined by rho in this fashion. So at any given time in the universe, we make a dichotomy rather than a continuum, dust and radiation. And both forms, as we know, are present in today's universe. There's the cosmic microwave background, which is certainly relativistic, and there are the WIMPs, which are certainly non-relativistic, and then there's the protons, but there's so few that they don't make any difference. This is certainly homogeneous. The rho is isotropic, as we said, in the co-moving frame, where the velocity of the dust grains, as seen by an observer on one of the dust grains, locally is 0. Of course, farther he sees them moving away, but in his neighborhood he sees nobody moving at all. And similarly, the radiation is homogeneous because the energy density is the same everywhere, and it's isotropic in that same co-moving frame. In that case, the spectrum is isotropic. Of course, if you are moving, you will see, just as we do, a blue shift in one direction and a red shift in the other, and you will know that you are not a co-moving observer. Our universe, as we said, is mostly dust with some radiation, and the important thing is that there's not a strong interaction between those two components. In other words, there is not ongoing conversion of cosmic microwave background energy into mass, or massive particles being annihilated and converting their energy into radiation. This is, of course, happening in stars, but that's a tiny fraction of the total mass of WIMPs in the universe, and therefore we're going to neglect it completely and assume that the total energy in matter is conserved and the total energy in radiation, appropriately defined, is conserved. And then you plug all that into Einstein's equation. Here's Einstein's equation as we wrote them. And the resulting equations are called the Friedmann equations. They were written down, as I said, in 1922 by Friedmann. And let's see what the simplifications are. Well, remember that the right-hand side of Einstein's equation describes energy and momentum density in the universe. So we know all about the energy and momentum density. They're isotropic. They're the same in all directions. They're homogeneous. The energy is determined by this function rho. The momentum is determined, it turns out, by the pressure. And so we can simplify, and Friedmann did, the form of the energy momentum tensor on the right-hand side using these simplification. What about the left-hand side? Well, the left-hand side is the curvature of space-time. This has two pieces in it. One of them is the curvature of space as part of the curvature of space-time. So there is this curvature of space if k is non-zero. Remember, we said k could either be 1, and we're talking about positive curvature, closed spaces, or 0, and we're talking about a flat space, or negative 1, and we're talking about this hyperbolic space in which geodesics diverge. And as I told you, don't tell anybody, but k is 0. We'll see why later. But there are additional contributions to the left-hand side, coming from the fact that when A changes, even if space is flat, space-time is not. As we will see, the change in A generates a contribution to space-time curvature, even in the case, as I told you, that space is flat. And so Friedmann takes this equation, takes these ideas, plugs them in, and he gets two equations. This is the first of the Friedmann equations. It relates the rate of change of A, remember A dot, divided by A squared. We have a name for the rate of change of A divided by A, that's the Hubble constant, and this can be a time-dependent quantity. Then this is given by, oh my goodness, this looks very, very familiar, 8 pi g over 3 rho of t, minus contribution from the curvature of space. Note this can have either sign. In our world, of course, we know that it vanishes because I told you already that k is 0, but this can have either sign depending if k is plus or minus 1 in the case of a curved space. So the only change to the dust world equations that we wrote, well, there are two real changes. One is that in rho, we have to include not only the energy density in the form of mass, but also the energy density in the form of radiation. We already sort of mentioned that when we talked about the cosmic microwave background. And there's an extra contribution from potential curvature of space, if space is curved, which, as I told you, it isn't. That is one equation that Friedmann writes. There is another equation. It's called the acceleration equation. It relates A double dot. What is A double dot? That is the rate of change of the rate of change of A. The rate of change of A at any given time is something, and the rate at which that changes is A double dot. If A were the position, then A dot would be velocity, and A double dot would be acceleration. So this has to do with the acceleration of the expansion. We didn't write this equation in the case of dust world, though we could have, and what we would have obtained is precisely the left-hand side here with p set to 0, as we did there. You are more than encouraged to write Newton's equation. A equals minus gmm over r squared. Apply it to the shell in dust world and find that this equation holds. I didn't write it because it gave us no new information, but here it does, because in this equation, unlike this equation, relativistic matter with non-zero pressure and slow dust type matter with zero pressure contribute differently, and it's bizarre. You would have naively expected pressure to notice that they both contribute with the same sign, and this is the same sign that we're familiar with. A has a negative second derivative. In other words, expansion is slowing. The rate of expansion, A dot, is decreasing, and this is due, of course, to gravitational attraction of matter, but also to the gravitational attraction of pressure. Is that a sign error? Does not pressure actually cause things to expand? Well, we're thinking about it wrong. First of all, pressure does cause a balloon inflated with high-pressure air to expand, but that's not pressure. That's a pressure gradient. That's the difference between the pressure inside and the pressure outside exerts a force and causes something to expand. In an infinite universe, where the pressure is everywhere the same, pressure is not applying any force. All the forces cancel, just as they do in the interior of a cup of water that's not going anywhere. On the other hand, the pressure, remember, reflects the fact that there is energy in, some of the energy density is in the form of the relativistic motion of the particles, and so that contributes to gravitational attraction, since all energy gravitates, and so in a photon gas, in a relativistic gas of matter interacting with gravity, pressure as well as density contribute to gravitational attraction. And so this tells us essentially something like the energy conservation equation that we had, and this is essentially Newton's law applied to this situation, and this one receives an extra contribution from the curvature of space, this one receives an extra contribution from the pressure of relativistic particles, but other than that, these are very familiar looking equations, and in particular, if we have a universe that is flat, k equals 0, and filled with dust, no p, this becomes almost exactly the equation that we wrote for a dust world. In fact, we can accommodate, since this contribution goes like 1 over a squared. Remember, in dust world, we had an equation that looked like h squared minus 8 pi g over 3 rho of t was equal to some epsilon prime over a of t squared. So just identifying epsilon prime with minus k r0 c squared. And notice that r0 here is the curvature at this time, not d0. It's nothing to do with particular shells. This is essentially the equation that we wrote in dust world, and the sign of k, notice flipped, is the opposite of the sign that we had there for epsilon. And so what we find is that if we have a non-relativistic universe full of dust, and if k is negative, in other words, if we're in the hyperbolic negatively curved case, that's the case where we found the solutions and expansion goes on forever. Whereas if we're in the case of a dust-filled universe on a closed k positive, so epsilon prime negative, all the shells were bound, and this is the case where the universe expands and collapses again. Whereas if k is 0, we're in the flat case, expansion continues but slows down. In all cases, the second derivative of a double dot, the acceleration of the expansion is negative, expansion is always slowing. Okay, energy conservation obtains in very similar ways. It's a property of these equations that energy is conserved, and so we obtain in the standard way that we already did in dust world that the dust or heavy non-relativistic energy density is diluted as the universe expands by a factor of volume, a cubed. We discussed that when we talked about conservation of mass there. This is in dust world, this is familiar, but the energy density in radiation behaves differently. The energy density in radiation is diluted more severely. It's diluted by a factor of a of t to the minus 4, and we understand it. Because if you have a collection of photons and their number density is the same everywhere, then as the universe expands, as some shell in the universe expands, well, some photons come out of it, but the same number of photons come into it from the other side. The total number of photons in that shell is conserved, but the volume of the shell has grown. That gives me a of t to the minus 3. But each of these photons has been redshifted, and so each carries less energy. So the net energy in photons, and also the net pressure, because those are proportional, is diluted not just by volume, but by an extra factor of a, or 1 over 1 plus z, due to the redshift, and that accounts for this minus 4. And again, both of these are valid so long as dust and energy do not exchange energy. In other words, so long as there's not massive annihilation of particle-antiparticle pairs into radiation, or massive absorption of radiation by matter, and that certainly neither of those is a cosmologically significant process in today's universe, so we can certainly make these assumptions. And we will discuss the consequences of this. We know some of the nature of the solutions. We'll have to discuss what the addition of pressure and possibly curvature does. But before that, these equations were written in 1922, and of course, Einstein was no fool. He knew that describing the universe is perhaps the best use of a theory of gravity. So once he was done with the precession of the perihelion of Mercury and the deflection of light, his next test of his theory was to try to understand the universe as a whole. But he was doing this in the early 20s when Friedmann wrote these equations. Remember, Hubble had not yet discovered that the universe was expanding. So Einstein was interested in a solution that described the world as he knew it. And the world as he knew it was just this equation with the Hubble constant set to 0, a static universe. So is that a solution? Well, sure, here we know how to do that. You can set the Hubble constant to 0 if you have a universe in which k is positive, so you have positive curvature, and this term just balances that term, and we get h equals 0, a dot is 0, the scale of the universe is not changing, it's a static, three-dimensional, closed, positively curved universe. However, this doesn't work. This would have worked, remember, an infinite, in that case flat, Newtonian universe with no expansion and uniform matter density might have been a solution of Newton's equations, depending how you do boundary conditions at infinity. In relativity, it fails. What fails is certainly we have managed to find a solution to this equation, but while h is 0, the rate of change of h is not 0. It is never 0 because the energy density is positive. The pressure, if any, is positive. This sign is negative. If expansion exists, it is slowing. But if you start with a universe that's not expanding, it accelerates in and it will eventually collapse. This was a terrible discovery. Einstein could not make his modified theory describe what Newton's theory had described so simply, a static universe, which is what he thought the universe was. So, Einstein, as I said, no fool, he found that he could modify his equation. He could make a modification to Einstein's equation by adding a term to it. He called it the cosmological term because it was added to address issues of cosmology. Again, this is the mathematical form of the equation. Instead of setting this property of space and time, this curvature collection, to be determined by the matter density in the universe, you just add another term, which is determined, the form of this is completely determined by the symmetries. You don't want to ruin the properties of Einstein's theory, but you get to pick this constant with dimensions, as we will see, of energy to the fourth in appropriate units, or 1 over area, I guess, in the units that we are working, and it's called the cosmological constant. And what Einstein realizes is that by adding this term, the equations are modified, and here in blue, I've indicated the modifications that the cosmological term makes to the equations. So now you can't quite balance rho against space curvature. You need to balance rho and cosmological constant, if positive, against space curvature. But by picking the cosmological constant to be positive, you can counter the negative contribution from here. This is very strange. What does it mean that the cosmological constant is countering the negative? Remember, that negative effect was the fact that everything gravitates, both energy density and pressure. So a positive cosmological constant acts kind of like anti-gravity. Not in the sense that things fly off the Earth, but in the sense that the universe as a whole, if lambda is positive, experiences an acceleration, a force on A, if you want, that drives accelerating expansion. That is what a positive cosmological constant does. From the form in which it appears in these two equations, you can see that you can mock this up by just interpreting this blue stuff. I've put it on the right-hand side. I can just equally, instead of putting it here, take a minus sign and stick it as a modification to the kinds of energy and momentum, the kinds of matter in the universe. So we can think of this cosmological term either as a change to Einstein's equation, or as the presence in the universe of some weird new kind of matter that is not dust and is not radiation. What is it? Well, we call it dark energy. We know that it actually exists. And its properties are, remember, it's determined by this one constant, just like, say, dust is determined by its energy density and then it's at rest. Radiation is determined by its energy density, and then its pressure is 3 over c squared times that. And cosmological matter, if you want to call it, or dark energy, is determined by this one number lambda, which can be positive or negative. Its energy density is related to this by this nice normalization, which allows us, which means that it shows up like this on the right-hand side. If you multiply by 8 pi g over 3 times rho lambda, you see that I can just stick this in as one of the forms. So now we have 3 types of energy density in the universe: matter, dust, slow stuff, non-relativistic; radiation, relativistic particles; and dark energy, whatever that is. And the density of dark energy is determined by the cosmological constant. But when I look over here, I see that indeed I can express the contribution here as a pressure due to the cosmological constant. And it is proportional to the energy density of the cosmological constant, just as for radiation, but it is negative. The cosmological constant applies a negative pressure. What is a negative pressure? Well, you can think quite reasonably of how a negative pressure would be created by a cosmological term. You can think of the cosmological constant as parametrizing basically the energy density of the vacuum. Now, how do you measure the energy density of the vacuum? That's kind of, in most situations, that's a silly thing. Imagine that every cubic meter of vacuum had, with nothing in it, had an energy of 10 trillion joules. Well, yeah, but how do you get out? You can't turn the vacuum into something else to get rid of that energy, because the vacuum is the lowest energy state of the universe. And that's exactly what we mean here. The lowest energy state of the universe, in the context of general relativity, its energy matters, and that energy density is measured by lambda with appropriate powers of c. Now, to detect that as a force, again, just like all pressures, I have to imagine that there was another vacuum, another kind of universe with a different value of lambda, say lambda equals 0. So if our vacuum has a positive energy density per unit volume, and there's another vacuum somewhere else that has a 0 energy density per unit volume, and you erect a wall between our universe and their universe, well, it's clear that because having our universe, our vacuum in this region in between the walls costs energy, the lowest energy configuration would be for their universe to squeeze our universe out, and for the whole world to be in the state with 0 energy density. Aha. So what that means is the existence of a positive energy is kind of like a negative pressure. It wants to squeeze down. That's the intuitive motivation I can give for how we understand that a positive energy and density of the universe generates a negative pressure, and a negative energy density, conversely, if rho is negative, which is allowed, if lambda is negative, contributes to a positive pressure. And what Einstein noted is that if he took lambda to be positive, then it contributed a negative pressure, which could cancel the contributions from here and could there lead to what we call today the static Einstein universe. It is indeed a model with k equals 1. It is filled with dust, so the pressure is 0, and space curvature and the cosmological constant, well, since p is 0, lambda is related to rho. You find here that because of the 8 pi 3 relative to the no factor of 2 here, we need 2 equal contributions to cancel the contribution here. One comes from here and the other comes from there. So this curvature of space with the unit of inverse area is equal to lambda in units of inverse area is given by this collection of rho. And so there's a family of them. For every density, you can make a static universe. Now, not long after writing this down, Einstein discovered that Hubble had experimentally measured that the universe was expanding. He also met with a man called Lemaitre, who had thought very deeply about the evolution of an expanding universe in the context of Einstein's equations, and realized that he actually had not needed to introduce this modification to the very pretty Einstein's equations. And he called it his biggest blunder. What we know today is that even when he blundered, Einstein was onto something.